Good evening. It's the last talk of the evening, so let's get this done. So to set some context, we want to share about how we've enabled fault tolerance training at Pinterest. We had some great talks today evening that spoke about how PyTorch gives you utilities for checkpointing. This is a story of how we made it available to our users. So I'm Karthik, and I have Chia-Wei. We're from the ML platform team at Pinterest. So yeah, let's get going. So the agenda, I'll just introduce what we do here, set the motivation, and then hand it off to Chia-Wei to talk about how we went about enabling fault tolerance training at Pinterest. At Pinterest, our mission is to bring everyone the vision to create a life they love. So Pinterest is powered by ML. We have both recommendation systems and content understanding models. As an example, let's take home feed. This is a classic recommendation model. We actually had another excellent session where my colleagues went over how we optimized serving the home feed models on longer sequences. In addition to recommendation models, we also have content understanding models. So here we actually index every pin, board in our corpus, extract rich information from them, and these are in turn used as features into our ranking models itself. So yeah, the TLDR is we have hundreds of ML engineers working on these problems, and in the ML Foundations org, we care about accelerating ML productivity, making sure ML engineers can move as fast as possible, support state-of-the-art ML applications, which is making sure ML engineers can train larger models, try out new modeling paradigms, and last but not least, keep our systems highly efficient so that we can operate at scale. So this is like a high-level diagram of how our ML training platform is laid out. We have broadly 3 layers. At the bottom layer, we have the ML compute substrate. We run on top of AWS. We use a combination of different types of GPUs depending on the workload. We have the A10Gs, L40S, A100s, and also H100s. We run on top of Kubernetes, so this is internally what we call our compute platform. So we support running Kubernetes, schedulers to make sure we can schedule ML training jobs. And on top of that, we have the ML runtime layer. So here we provide an SDK on top of PyTorch that ML engineers use to author their ML applications. So here we're providing common utilities that ML engineers can use to run their ML training jobs. So this could be things like an optimized data loader, utilities for checkmarking their models, integrations with our experiment tracking stack, exporting models into TOT scripts so that it can be served. I want to say about 99% of our recommendation and content understanding models are using this. So that being said, why do we want to solve fault tolerance? Of course, we all know this. When we run training jobs on these expensive GPU machines, things can go bad. Our Kubernetes team can do cluster rotations. We can have bad GPUs. We've seen S3 flakiness issues. So when these happens, we don't want all the compute that the model has spent to be wasted. So from a cost efficiency standpoint, recovering all that work is helpful. But the second motivation is also to use GPUs more opportunistically. So we keep our model of giving out GPUs pretty simple today. So what we do is every team has a pool of GPUs that they reserve to use. But what we've seen over time is that not everyone uses their GPUs fully. Sometimes there are periods where they don't use it well. So across the board, there is some slack in terms of how much GPUs get used. So we want to be in a world where teams can use GPUs opportunistically. And for that to happen at scale, we actually need these jobs to be preemptible, so that when the team that owns the GPUs needs their GPUs back, we can just kick off the jobs that are using these GPUs, which means these jobs need to be fault tolerant. And as we think about using GPUs opportunistically, there's also the opportunity to use GPUs from the serving side. We have this pattern where GPUs have this period of time where we don't have users, so there is a trough of time where GPUs don't get utilized, so it'll be great for training GPUs to use these. Again, the same problem presents itself, so where we have training jobs to use these GPUs. However, when serving wants it back, we want to kick these GPUs out and then offer it to serving. Again, we want these jobs to be fault tolerant so that they can now resume their work on another GPU. So that being said, I'll hand it over to Chia-Wei to talk about how we enable fault tolerant training.
Thank you. Hello, everyone. I'm Chia-Wei. I'm going to talk about the key challenges next. So people might think about like checkpointing is just like a straightforward diagram on the right. In the typical multi-epoch training, each epoch iterates over the data loader. Every mini batch goes through forward, loss, backward, and optimize. After the data set is exhausted, we write a checkpoint and then continue to the next epoch. But this approach isn't ideal when a single epoch takes a lot, like long time, right? On the order of days. So we need a strategy of like mid-epoch checkpointing. A simple approach is just to save the current iterations every n steps so that on the restart, the job can fast forward and then resume from that point. However, this comes with some drawbacks, right? During fast forward, GPU sits idle, especially for data loader, boundary jobs that fetch thousands of features from the data store with streaming fashions, and sometimes they even have to perform like heavy pre-processing. Notably, meta reports in like 2022 found that resuming large language models training from the checkpoint requires replaying the data, like, which is not desired for wasting those GPU. So we need a way to reliably do the checkpoint, mid-epoch checkpointing to persist the state of the data loader as well, especially when we streaming from external storage, so that on resume we neither repeat it or skip the samples that we care about. We began to see industry movement toward stateful data loader, like Mosaic AIs have a streaming data set, which was early options, but it imposed a conversions of like, you have to convert your data to the Mosaic data shards, which can be like costly or undesirable if you already have a certain pattern of like data store at the company. So on the other hand, 2024, Torch Data introduced a new library called stateful data loader that became our preferred solutions thanks to its flexibility and lightweight interface. Without we don't have to like change data format just to use those. Another aspect of like why not multi-epoch training is like in recommendation systems world, there's a paper called like toward understanding the overfitting phenomenon of deep click-through rate, which basically highlights that whenever for large-scale recommendation system training, whenever you across the like second epoch, a lot of time you're facing the overfitting issues, so making additional epoch less useful, which reinforce the value of like mid-epoch checkpoint. Moreover, when data set of message and compute is limited, the cost of like multi-epoch training will just be not ideal because we want to like get reasonable amount of model quality within the time. Another challenge for us is we're not just using Torch data loader. A lot of recent trend at Pinterest is to adopt array for data loader. The array allowed us to do like horizontally scale on the CPU workers, so data loader will no longer be the bottleneck of training, which is nice. And we also use array for a lot of works like last mile data processing, where we move some of the data pre-prod works from Spark to array. So ML engineers are able to iterate much faster in their training job instead of doing the disaggregated data ETL in a workflow fashion. Those sounds pretty great, but it also gave us a bit headache about how to reliably checkpoint the state of array data. One key difference between array and PyTorch is that array is much dynamic in terms of number of workers during data loading. In Torch data loader, what we do is usually predefine number of data load workers per GPU, but in array, it depends on many factors like the current available cluster resource, the back pressure in your data pipeline, and so there's no easy way to store and restore the state of array data as a snapshot. Although array data itself has some fault tolerant semantic like it can reconstruct the object stored data using a lineage upon failure. But in reality, some failure could be non-retrievable or even happens in the GPU ranker side. So once that happens, the entire array application will fail, and we lose all the states that in array cluster, array data site. So let's talk about how do we solve those here. First of all, let's talk about the torch data loader part at Pinterest, or we have a streaming data loader. Looks like right-hand side. It's an oversimplified version, but as you can see, for each GPU workers will have its own data loader, while data loader will spawn up multiple processes and shard across the data set. For each data workers, we will initialize it with subset of files, and then it could load from S3 in the streaming fashions. Noticeably, we also maintain an in-memory shuffle queue for each worker. So when we load the data from S3, we actually can load multiple files at the same time and then do the in-place shuffle, which gives us some randomize across the data set. This is quite important for model quality during the training. So from this setup, we noticed that there are a few states needs to be taken care of, right? The first one is just the state of like, what is the current file, what is the file that's owned by these workers, and the second one is the in-memory shuffle queue, because they also have some data that reside inside those queue, and we don't want to be loose after restore. So stateful data loader perfectly fade out need, where it allowed us to do checkpoint every n steps by implementing the state date and low state date, where we can store all the state that we care about and then restore it accurately later on. It's also lightweight that we can be implementing for arbitrary iterable data set, as long as we can provide the state date and low state date implementation. So this is roughly like the high level structure of like how we do the checkpoint. Like data loader will dump the checkpoint, as well as the trainer side, the model, optimizer, learning rate, stuff like that. However, there are some learnings behind the scene. So stateful data loader, although it allows us to do the state take, the states that transfer across is actually transferred across the process. So let's say you have a main process that codes state take, and what behind the scenes, like every workers will gather the states from itself and then do an inter-process communication back to the main process. So every state here has to be pickable. And it also introduced some memory overhead. If you think about like pickle arbitrary object in Python, the size of it can be large if it's like non-primitive type. So we actually run into an issue like for in-memory shuffle queue. Remember, we have that queue for like persisting some of the data that for shuffling. And in those data type, we're using a list of like pi error table. So if we naively pickle that data into like file or some like pickable format, it will be like 300 times larger than itself. Like in memory is like 100 megabytes, but it will grow to 30 gigabytes if we just naively dump that as a pickle file. So what we end up doing is, instead of using pickle, we use the pi error IPC serialization protocol that dump that file locally first, and then instead of transfer that state back to the main process, we just do a two-stage persist. We first write it to the like S3 or whatever external storage, then we get the S3 pass back. So what we end up passing back to the main process is it's only just a string that what is the S3 pass that you have to like look up later. And it helps us to speed up like 500x when we're doing the uploading, and also the 300x size reductions that we're able to prevent out of memory happens when we're doing the low state dig. For array data loader, there isn't a straightforward way for us to do checkpoint, so we simulate checkpoints by splitting the data set into unlogical subset and only saving progress at the boundary between them. So concretely, we process one subset at a time, and then checkpoint once that's finished. We track the progress so in this case, we only need to check the epoch and virtual epoch states, where epoch is the real training epoch, virtual epoch is just the index of the current sub-data set within the epoch. This keeps the design simple, avoid dealing with the data loader states for array data, and it can work well with both array data and torch data loader. But the trade-off is like we're introducing some overhead when switching the sub-data set, and I will talk about some of the overhead later. And also there's one assumption here, like we assume all the data can be kind of logically split into pieces, which may not be true for example, we're using like a iceberg table as a data source, then that could be an issue for you to split that. Another highlight for us is we implement a checkpoint manager, which abstract out the underneath mechanism, so users don't have to know how the checkpoint is working. We integrated data tracking using weights and bias for visualizations. And for the load and save events, we will write the metadata to Parquet table for offline analysis and auditing. This gives us a centralized place to enforce best practice and monitor usage, and centralize how checkpoints are created, stored, and restored, improving, reduce the overhead of users to memorize how to do like checkpoint in the right way. And this is true for like distributed, for example, distributed model parallelism. A lot of time, the model itself is lazy loaded, lazy initialized. So you have to do like a dummy first fast forward to initialize the model parameters, and then you do a reload. So this kind of like different scenario training type, we don't want users to be really understand how to do that, and we handle that behind the model like checkpoint manager within our training loop. And to make the adoption much seamless, we implement, we already have some existing like training loop or like solver, we call it at Pinterest. We just implement the drop-in replacement for like fault tolerance X solver. Then users can ideally just do one line replacement, and then they can enjoy the benefit of fault tolerance. And this is important because we have like 80 of projects, 400 of trainers, 900 of use case across 3 orgs. So to make the adoption much seamless, we need to make sure that the overhead for users is like minimum as possible. Another aspect that we do for fault tolerance is, remember we have like workflow failures can happen, and whenever that happens, we will tear down the job itself. So we made operator itself fault tolerance as well, avoid disruption from graceful interruptions, system failures, or pod deletions. We do it by just persisting the like job state, such as project, job identifiers, and related metadata into MySQL database, enable the operators to detect, interrupt, and then resume from the last known state rather than restarting from scratch. And this significantly improves the reliable and reduce the waste compute that happens on the workflow side. Okay, I'm going to share some early results. Here are a few representative use cases that have benefit from our approach. OmiSage, which is our multi-entity heterogeneous graph representation learning, and PinClip, it's a multi-modality vision text embedding model, and also some torch rack for related pins ranking, ads engagement. All of those are using our framework to do the fault tolerance training right now. And on the right-hand side, you can see like those laws and like time series data can smoothly connect to each other because we take care of the like data load the states, the model checkpoint correctly for users. They don't have to worry about what happens. So I also want to talk about some overhead that we observe from our approach. We measure the overhead of each approach from existing use case. With Ray data loader using virtual epoch, the cost is about like 0.8% per subset. With virtual epoch, set up like 10, and each epoch is training for 12 hours. So this gives us an insight, like it's probably works much better for a larger data set. For PyTorch data loader, it's surprisingly much better because the overhead is just like 0.3. So it fits for most of the use case at Pinterest. We also track the adoption and emit those saving metrics upon loading checkpoints so both platform and users can easily see the visualizations. And this is just some of the reports that we will generate daily for users to see like how much of progress they made, how much progress they saved by adopting those. Cool. And along the way, we learned that fault tolerance isn't just a library or features that provided at the runtime level. It's an end-to-end experience for users, spanning from configurations, training loop, checkpoint management, seamless resume from either UI or workflow systems. To support this, we also built a diagnosis pipeline that aggregated like application logs, Kubernetes events, infrastructure time series data, and external service health data fit into our diagnosis service to determine whether job is failed due to platform issues. And with that, we're able to like smartly tell the users, hey, your job can be retried on pub. Even we can help users to retry on behalf of them. Yeah, so that's just some of the progress we made. And this is kind of like the UI I mentioned. Like we provide this UI for users to easily retry whenever this failure happens, and they can just enjoy the fault tolerance benefit behind the scene. Looking ahead, we'll focus on 3 areas: functionality, like we want to add. Remember we talked about like Ray data loader have some limitation on the, like you have to logically split your data. We want to make that patterns more generic. So even let's say you're doing like a iceberg bucket join, you are able to do that in a non-file-based virtual epoch. And we also want to grow the adoption for other training framework in-house. We have a LLM, VLM fine-tuning pipeline. We want to use that for more adoptions. And for performance-wise, we want to improve the overhead of switching data set between the virtual epoch, and also start to use the distributed checkpoint that Torch provided. Sometimes we can provide like a async checkpoint, so for people that don't really care about strong consistency, they can just use that as a flag. We also want to look into like Torch FT, which is another project like just open source recently, and it sounds very interesting, and we would like to see how we can introduce that into our framework. And cool, I want to thanks to a lot of team members and the customers that's helping us to make this happen. And cool. Thank you. That's it.
Thanks for sharing. I just have a quick question. You mentioned like there is lots of work you have done to make to like checkpointing the like data loader's status. I'm just curious, is that like just a augment into read data, or like it's also like some augment you have done into the stateful data loader which offered from PyTorch, or actually you are just using like PyTorch native data loader with read together? Yeah.
For us, mostly we just use the stateful data loader out of the box. We don't have to do too much customizations. We try to do some, but we realize that it's already doing some like, so the way that it do checkpoint is not doing like every steps. You can do like n steps. So it's also doing like delta checkpoint stuff. So itself is already like very efficient.
Thanks for talk. So I'm wondering, how do you checkpoint for the training worker and the data worker at the same time, or you are doing that asynchronously? Because like some data might be losing, right, if we are checking point at different time.
Yeah, that's a good question. So we usually do synchronization checkpoint. For data loader and the model, we will do it at the same time. We don't do like a different periodic for different data loader or model checkpoint. They happens at the same time. Is that the question you're?
I see. So you mean like you have a synchronizing checkpointing after?
Yes, right now it's synchronized, but we plan to do like async by using the distributed checkpoint.
Got it.
That
okay.
Torch have.
Got it. Thanks.
Get the fault tolerance.
Could you repeat it?
Yeah. The database that you showed in the fault tolerance section for restoring the job state, is that part of the Airflow setup where it stores the job info as part of the job status and everything as part of its metadata, or is that something you have to do additional on top of that?
Yeah, so Torch stateful data loader only provide the interface for you. You have to implement your own implementation, like what is the states that you care about. For us, we have different states, and depending on the type of it, you also have to see how to optimize that to save as a state.
I think if it's Airflow, we do use the metadata that comes with it. So our workflow team, they have a way for us to persist arbitrary data into their.
I see. Yeah, that's the point I was trying to get at. Okay. Yeah. And one follow-up question. I think you also mentioned that in the future work you're trying to bring functionality for pre-training, for fine-tuning. Does that mean basically using the same ML ENV SDK to allow people to fine-tune an existing model, not just train from the ground up?
Yeah. So we do have some fine-tuning support in our ML and SDK itself. So that's the entry point. So if we do support fine-tuning, it'll be through the same SDK. I think fine-tuning is slightly simpler because they do train across multiple epochs. So the amount of state you have to save is just the epoch number and the model checkpoint.
Okay. Yeah. Thank you.
Any more questions?
Is there a reason you're pickling and not just storing the parameters as tensors and then reload the tensors, reload the parameters into a newly initialized DMP?
Is the question about how do we do the reload, or
why do you do the Python pickling of your model into the checkpoint instead of just storing in the parameters as tensors and then reloading it into a newly initialized model?
Right, I didn't get the question. Could I?
So DMP gives you load state dict. So you could just supply the tensor. So effectively in your checkpoint, you don't need pickled objects. You could just store the tensors as parameters, as serialized.
Oh, I see. So sometimes the state itself couldn't be a tensor. So for example, if you're doing a custom data transform in your data pipeline, then the way that your in-memory queue could store something arbitrary, right? So we have to find the right way to optimize that instead of just put it as a tensor. And also sometimes tensor can be quite large to transfer back in memory. So we also want to see be mindful about the memory consumptions when we do the checkpoint.